Welcome back to lecture, everyone. We're going to continue with our study of the chi-square distribution and applications. So I'm going to get rid of me. Welcome back, and let's get started. So this time we did a goodness of fit last time. That was section 10.1. This is basically a test for independence and homogeneity. We're going to kind of do something similar, but these are going to be based on a table, where the other one was just a simple list, and then we kind of expanded there. Here we start with a table. We're going to go to another table for our expected values. So again, remember our contingency tables. Here, take a look at this one. Do some college majors require more studying than others? The table below shows the results from the National Survey of Student Engagement Survey, where a sample of 1,000 college freshmen were asked their major and the average number of hours per week spent studying. The table is called a contingency table. We've looked at that in the past, and we spent some time calculating frequencies, probabilities based on this. Here are the frequencies inside, and then we build probabilities based on this. Okay. So a contingency table relates to qualitative variables. One of the variables called the row variable, these are rows, has one category for each row of the table. So here's a category 0 to 10, 11 to 20, more than 20. And then our column variables set up a different category for like the humanities, social sciences, business, and engineering. So we can look at the hours studying per week based on the different criteria, the different majors. The total number of individuals in the table 1,000 is called the grand total. We usually put that down here in this corner. We sum along the rows. We put our sum here, here, and here. Then we sum along the columns. And then the column, if we add up all of those column sums, we get the total. These row sums will also be that very same total. In fact, that's a check. So what we're going to do is look at this thing and determine, this is called a test for independence. So what we're going to see is, does it matter how many hours you're studying to meet? Does the major, the number of studying hours per week, does that depend on the major, or is it basically independent? These are 0 to 10. These numbers are all very similar, that there's no major difference. Okay, so more than 20, does it matter? 11 to 20. So that's if it doesn't matter depending on the major, then they're independent. If studying the number of hours to weeks depends on your major, these things are probably going to show up. Maybe social sciences would be less, engineering I would expect to be more, maybe the other way. Okay. So in the survey about major and hours spent studying, if these variables are independent, then the distribution of hours studied will be the same for all majors, and the distributions of majors will be the same for all categories of hours studied. So no matter if we picked here, it wouldn't matter, and then if we picked here, it wouldn't matter. So they're basically independent. So what we're going to do is a general statement for a test of independence. Remember before we had to give, here's the probabilities that match the probabilities. P1 is equal to this, P2 is equal to that. That was a goodness of fit. Here we're just going to make, for a test of independence, we're going to make one general study. We're going to say that the null hypothesis is that the hour studying and major are independent. Doesn't matter between hour studying and major. It doesn't matter. Okay. The alternate, hour studying, and major are not independent. Okay, so we don't have to worry about H1 giving us left tail, right tail, two tail, because we're going to use the chi-square statistic, and that's always a right tail test. Remember, we added up the contribution differences from what the observed from the expected, and that built our chi-square test statistic. Well, we're going to do that based on the very same thing. Okay. So what do we do? Once we built it, so if we go down here, let me see if I can get this. So we're going to go down here. Oop. So we're going to come out with our chi-squared distribution, right? Here's our critical value. We're going to do our test statistic, and if it's out here, that's the rejection region. Failed to reject, this starts at 0 and then goes on out. So if the difference between the observed and the expected starts getting further and further away, we're going to go into this rejection region. And who are we rejecting? H0. So if we reject H0, if we reject this being independent, then we conclude that they are not independent or dependent. Okay, that's the rejection. So the null hypothesis states that our setting and majors are independent. So what we're going to do, remember the probability multiplication rule, that if they're independent events, and here's what we're going to do. Let me go back up here. We'll go back up here. For independent events, the probability A and B, two things. If they're independent, well, that's just the probability of A times the probability of B. Okay, so what we're going to do, this is going to be our columns. One way is like our A's, this is our B. So the probability of a humanities would be the 257 over 1,000. The probability of it being 0 and 10 would be the 345 over the 1,000. So this probability in here would be just the product of the 257 over 1,000 and the 345 over 1,000. Okay. So that is how we're going to get the probability from each one. And if we know the probability, well, what's the expected value? It's n. Expected value is just n times the probability. This is the probability. Our n is the 1,000, and we just have to multiply together. And notice that one of these kind of goes out, and it's always going to be the very same thing of just this times this divided by 1,000, or whatever number this is. So if this was an n and an n, it would be this over the n. Okay, so that's the first expected frequency. Each one is just the row total. Here's the row total. You remember that was at the end of the row. Column total was at the bottom of the total. And over here, the grand total, if I add it up this way or add it up this way, I get the grand total. I don't add these up twice. These I've added up. It's just a different way that I'm adding. Okay. And then that's just the expected value. Okay. So here's our setup. And I'm going to go into Excel in just a minute, and we'll kind of look at how we actually can do this a little easier. State the null and alternate hypothesis. We've got that. Independent versus not independent or dependent. I compute the row and column tables. I always want to do that when I'm computing probabilities based on contingency tables. Here's the expected value. The probability would be row total times column total divided by the grand total squared. Remember, this would be grand total and grand total. So, but we're going to multiply times the grand total, and that'll give us the row total, column total, over the grand total. Okay. So now once we get that, we're going to choose a level of significance alpha. We're going to compute our test statistic. These are the same thing as it looked before. The sum of the difference between the observed and the expected squared divided by the expected value. Here's something a little new now. We're going to do the critical value. Remember, we had to do something like, let me see if I can draw that real straight. Here's what our chi-squared distribution would look like. There's our chi-squared distribution. And this CV, the critical value, depends on the degrees of freedom, right? Before, it was categories, cat -1. Well, this is the row -1, columns -1. And that's the degrees of freedom. And then we basically do this thing. Where's that guy? The test statistic. Is it in here? Is it in here? We fail to reject. Here we reject. And then we state a conclusion. This is easier. If we reject it, we reject independence. If we fail to reject, we fail to reject. There's insufficient evidence to reject independence, is what we say. It's a very soft. Okay? So perform a test of the null hypothesis that majors in our setting are independent. Use alpha as 0.01. So here's what we're going to do. There's our null and alternate. They're always for independence. Chi-squared independence is always H0 independent, H1 not independent. So I'm going to switch out of this. Yeah, for the time being, that's fine. I want to go over and I want to kind of look at what I would do if this was Excel. If I did this in Excel, I would go through, set up my table again. These were it. Here, I would just do some of these things. And then as long as I'm summing here, I can drag. When I drag, that just comes over these things. Here, B2 through B4, and then I would pull it along this way to give me C2, C4, all of those. And then this is either this down here or this down here would give me the same number, 1,000. Okay. So now, all I would do was transfer. These were, again, these were the actuals. See, these were the actuals. I would transfer these numbers. All I did was just type these in. So I'd have row totals. I would have a grand total. And now I let Excel do the calculation for me. So I said here, I said, oh, this is J5 times this divided by the grand total. So it's the row total times the column total, either way, column total, row total, divided by this once. The probability would be divided by 1,000 squared, but since I'm doing expected value, I would multiply the probability times 1,000, so it's only over one of these things. Once I did this, I kind of spread it across, used dollar signs so that they wouldn't as I went here. So if I did J5, this is K5, L5 here. It is multiplying the M5 always times this divided by always that. And I kind of set these things up and just built a row at a time or a column at a time to give me these numbers. Now all of these are the expected values based on what we saw in those rows. And then I went down here and I just said, this is what this is. It is this one. So let's look at here. It is B2. That is the observed value minus my expected value squared divided by the expected value. And once I did that, all of these, once I drag sideways, I get it. I go column wise. It knows to do my columns. Everything is lined up. So I got everything this, and this was just the bottom was just a sum of these. This one was the sum of these. This one was some of these, and I just summed these up to give me the 34.63775. While it seems to be a lot of work in Excel, all I did was set up the pattern and let it go. If I didn't, I would have to go through, build these with each calculator. This times this divided by this, this times this divided by that, and build up. This one would be this times that, the 4, 3, and the 3 or 9 divided by the 1,000. So for each one of those, you would have to go through, calculate the expected value. Those would be the expected frequencies, and then I'd have to add up all of those. Sorry, add up the difference. They put these, here is the expected, here was the observed, and they just went through and said, now I'm going to take observed minus expected squared over the expected and adding them up from each one of these categories. Each one of these little things right here is called a contribution. Okay, so what about the critical value? Here was our 34.638. We saw that in Excel as well as what they got. But what about the critical value? So we had 3 rows, 4 columns. I subtract 1 from each. 2 times 3 is 6. There's my degrees of freedom. The significance levels was 0.01, so I'm going here and here. That would be 16.812. And now let's draw our picture. I'm going to draw it right over here. Let's see if I can get it straight. There. And here is basically a chi-squared picture. I'm going to draw this somewhere along in here. This would be the C critical value 16.812. I'm just going to draw a little line that says that represents that. Here's 0. And our chi-squared was 34.82. Somewhere out here, twice that, 34.638. Rejection region, always in the tail. Failed to reject is that main body. It was in the rejection region, so we reject. So reject. Who do we reject? Always H0. And in this case, the H0 says we reject independence. Okay. So we conclude that the choice of major and the number of hours spent studying are not independent. In our general words, we would say there is sufficient evidence to support that, to support the hypothesis that the rows and columns are dependent. Or equivalently, there's sufficient evidence to reject the hypothesis that these are independent. Okay, so Excel, you saw how to do it in Excel. If you were doing, you could also do this whole thing on the TI-84 by selecting this chi-square test. It expects that you've got all of your stuff. You remember your L1, L2 table, L3, L4. It expects all of these things to be filled out to the same level. So this is your whole contingency table. Okay. TI-84P. That would be your contingency. You just enter. Select your chi-square test. And then go down here and do, oh, I'm sorry. Let's get rid of this. You would enter this into your A. This, your expected, is your B, and it will calculate the B from your A. So we don't do this with L1s. Yeah. So you will have to do matrix operations, create your matrix. You will do whatever the size are, create this at a certain size, and then start entering them in the array. Okay. So if we were going to do this, hold on just a second. So if we were going to perform the hypothesis test for independence on the TI-84, we would go down here, select the chi-square test. You see this observed and expected. All we need to do is create matrix A. So rows by columns, these are rows and columns. Enter this thing out. Start entering these. These were the observed. So enter all of those. It will say the expected's in B. It will create this B for you so you don't have to do the expected. It knows what the probabilities and the expected values are. It goes ahead, calculates everything from the grand total, set of row totals to column totals, and just do a calculate, and then that'll give it for you. Okay, so let's kind of walk through here. Create a matrix A, set the size, 3 rows, 4 columns, enter these things in here. Do a chi-square test, let it know that it's A. This B needs to be cleared. Delete previous B matrix. You could have different values of probabilities here with expected values not based on independence, but it could still do a chi-square test. So if you have this, it will base this, they've already given me the E, they won't calculate it. So you need to delete this, but it's going to be in here, not there. So you would go under your matrix operations, delete that matrix B. It'll create the B and fill it in with the expected, and then it'll calculate. So once you do your calculate, here's the output. And this is what you need to know if you were given this on a test. There's the chi-squared, that's the test statistic from what you entered into A. The probability 5.0 e to the negative 6, what does that mean? Your p-val is 0.000123456. So you moved over 1, 2, 3, 4, 5, 6, and then the 0.064. So that is less than your alpha. Alpha was 0.01. That was back up here. That is less, so reject H0. The p-val less than alpha, reject who? Always the null hypothesis. There's another term for this thing, but it's kind of the same thing. It's called a test of homogeneity. It is the very same thing, but you will see how this one makes a little more sense in this terms. So in the contingency table we have seen so far, the individuals in the table were sampled from a single population. For each individual, the values of both the row and column variables were random. Same population sampled. So in some cases, values of one of the variables, say the row values, are assigned by the investigator and are not random. Okay. So in these cases, what we're going to do is do a test of homogeneity. So they're different places, and you're going to see why this is going to be true in just a minute when we take a look at it. Okay. But what we're going to do in that case is look at it and basically say that the distribution is the same for each row, basically independent, even though they are from a different sample. So it's going to be the same thing, but we need to call it something different just to let people know and the way it's set up. Okay, so let's look. What we're going to do, here's the big catch on this. The method for performing a test of homogeneity is identical to the test of independence. This is what we did. We said that the columns were independent, basically that these were independent from from each other. But now, why do we consider this one different? So here we're going to have something that's not from the same population. We had a group of people, we just looked at just a random group of people, and here they had different things going on, okay? Some of them, so let's take a look at this. Test the hypothesis that the distribution of outcomes is the same, they're homogeneous, is the same for all three treatment groups in the example about the drugs telmisartan and rampirol, okay? This, we have three different treatments, and then we're going to look at different categories, and what we're going to say here is basically, is there any difference between these drugs? We're going to assume that these things here didn't matter whether you had this one, or both drugs. You know, they're going to be different numbers. That's just sampling theory, right? Just depending on the people, but out of the general, if you keep doing this over and over, are these independent, are basically homogeneous? Didn't matter which ones. Now, if we come by, we reject it, then we're saying that some treatment had a different effect on these columns right here. Okay. Null hypothesis says the distribution of outcomes is the same for all drug treatments. Okay. The alternate hypothesis says that the distribution of outcomes is not the same for all treatments. Okay. There's no difference in these treatments between if you have one of these. Okay. So how are we going to do it? The very same way. We're going to go here. We're going to add some this way to get a row total for each case. We're going to sum this away to get column totals. And then the expected frequencies, what are these? The expected value for this one would be that row total. So for this guy, this times that divided by that. Row total times column total divided by the grand total for each case. Okay, so here we wrote, here was the observed. These are the expected. So now you have to go through and add up the differences squared, 598 minus 607.1, divided by the grand total. Here's the grand total, 70. The grand total was... I'm sorry, over the expected. For each one, expected, we add those up, we get the chi-squared test statistic. I like to put this down as the test statistic. It's 2.259. We have 3 columns, 3 rows, don't include the sum, don't include the sum, no, just this by this. 2 by 2 is 4 degrees of freedom. So I'm going to go here to degrees of freedom equal to 4. What are we testing it at? Alpha 0.05. There's the area in the right tail. And these, where this thing's cross, that's the critical value. So CV 9.488. So here is the chi-squared, that's the 2.259. Failed to reject. And what does that, what was the H0? It says that the distribution of outcomes is the same for all drug treatments. So we cannot reject this. Okay. So there is insufficient evidence to reject conclude that they're different, or to reject, there's insufficient evidence to reject that the distribution's outcomes is the same. So there's two different ways of saying the thing. We can't conclude that they're different. We can't reject the possibility that they're the same. Okay. So go through again. You're going to have two different versions, a goodness of fit, and that's just based on some observed 1, observed 2, observed 3, observed 4, observed 5. I have some probabilities. They could all be the same. I could specify, but now I'm basing each one of the expected E1 is equal to NP1, NP2, NP3, NP4, NP5. So I get this, and now the chi-squared, this was for the goodness of fit. The very same formula, observed minus expected squared over the expected. Add up all of these differences here and put them in. And then we went to the independence, where the expected is just row total times the column total divided by the grand total. Okay. H0 independent / homogeneous. There's no difference among those treatments. And then H1 dependent. They are not homogeneous. The outcome depends upon treatment. Okay, between those two. Okay. So again, go through the slides, go through the book, read the material. There's some extra material, supplemental. There is slides, multimedia examples up in the textbook on the electronic version. And we'll see you next time. Should see you later. Bye.